Greetings and what I don't like saying greetings, but there I did. We're going to talk about antiderivatives of formulas, section 3.3. So, chapter 3 is all about integrals, aka antiderivatives. Chapter 2, remember, was all about derivatives. Anti-integrals? I've never heard them called that, but you could. All right, and so that's where we're at right here. We've introduced the idea of an antiderivative. An integral, definite integral, or an antiderivative is like the area under the curve. The antiderivative of a rate of change is the total change. But we haven't really talked too much about just how to find it. Sure, an antiderivative is kind of like going backwards from a derivative, but how do we actually do that? And that's what we're doing in this section. So you've seen this before, that if big F is an antiderivative of little f, again, what that means is that the derivative of big is little, antiderivative of little is big. That's how the two definitions are connected. Then the fundamental theorem of calculus tells us that the definite integral of that rate of change is the total change of its antiderivative. Okay, so what we're going to do in this section is figure out how to find this f so we can evaluate this integral. So another way to do that, in general, what we're doing in this section is we're filling in the blank. To find big F, all we have to do is fill in the blank to say, okay, what do we have to take the derivative of in order to get little f? Because that thing up here will be our big F, our antiderivative. So look, this is everything on the left is your derivative rules from 2.5. I said all we have to do is fill in the blank, and you can see really that we are filling in the blank right here. Okay, so the antiderivative, KF is the antiderivative of KF prime. So all of these rules that we have from chapter 2, we're going to have a very similar rule in chapter 3. Everything over here is old. None of this is new stuff. Everything over here is the new version. So if we want to take, remember, the derivative of a constant times a function, that was just a constant times the derivative. It's the same thing for integrals. The integral of a constant times a function is just the constant times the integral. So the constant multiple rule, basically the same for chapter 2 and chapter 3. Sum and difference rule, basically the same. If we want to take the derivative of two things added to each other, we just add their derivatives together. The integral of two things added to each other, just add their integrals together. So a ton of these rules that we've already learned apply to integrals too. The product rule and quotient rule, that's a little bit more confusing. We'll talk about the product rule in 3.4, our next section, but don't worry about those just yet. The power rule, very similar. If we want to take the derivative of like x to some power, we would bring down the power and then subtract a power. Well, we have something very similar for integrals, but we're kind of going backwards. We add a power first instead of subtracting, and then we divide by that new power. And you can check any integral is an antiderivative, right? You can check any of these formulas by taking the derivative. What is the derivative of x to the n plus 1 over n plus 1? Well, we use the power rule. N plus 1 comes down, and oh dear, hold on. N plus 1 comes down. No, this always happens to me. Great. We subtract an exponent, and we still have the n plus 1 from before. And you can see that when we take the derivative of our antiderivative, we're going to get back our original function. That's always going to be the case. We can always check our answers with all these antiderivatives by just taking the derivative of our answer. And then again, remember that there are infinitely many of these. So we have plus c. C is any constant. Okay. And this power rule works for any exponent, literally any exponent, fractional, negative, any number, real number you can think of, except for -1. The exponent's -1, this formula won't work, but for every other one, it'll work. What happens when the exponent's -1? You won't have to wait long to find out that answer. We'll get tons of practice with this in the future videos, just kind of introducing them. Again, over here, what was the derivative of an exponential function? Itself. So what do you think the antiderivative of an exponential function is? Antiderivatives are all about just going backwards. So if the derivative of e to the x is itself, the antiderivative of e to the x should also be itself. And you can see that we do have that right here as well. And again, plus any constant. We're not going to do this one very much, but you can see a very similar formula. The derivative has us multiply by a natural log of a. Well, the integral is like the backwards. What's the backwards of multiplying? Dividing. So we divide by the ln of a. And I promised you would find out, and you don't have to wait very long. Power rule doesn't work for -1. If we have an exponent of -1 and we want to integrate it, it's also, that's, x to the -1 is the same thing as 1 over x. That's the natural log of the absolute value of x. This one's a little weird for why the absolute value is there. There's a reason. It's probably not worth talking about in this video. But these basically undo each other. The only difference is that their domains are a little different. And that's why the absolute value is in this one. So this is short and fast rules for integration. All the rules for integration we're talking about in this section are just integral versions of the derivative rules that we've talked about in 2.5. So all of these come in pairs. Old is on the left, new is on the right. Next video, we'll actually do some integrals and get some more practice, but this is kind of a good introduction for what these rules mean, what we're doing, where we're at. Let me know if you have any questions.